Good evening, all. Welcome to Basic Electronics class once again.
Good evening, sir.
Good evening.
Good evening, sir.
Good evening, sir.
Good evening. How many of you have joined? Around. Okay, so let the others join in. So let us quickly start off with the session, and maybe the others can join and participate. So if you remember on last day's class, we had started off actually a very important discussion on semiconductor, where we had primarily discussed upon concepts related to yeah related to junction diode, okay, compensation doping, as well as how the nature of forward bias and reverse bias will affect the nature of our current conduction. So let me just share you that first, and maybe I'll just go about doing it. So this was the discussion that we had, and I had told you that any of the semiconductor or the intrinsic semiconductor can be made in the other way around if we can inject more and more doping, either in terms of the donor contribution or in terms of the acceptor contribution. And keeping that in mind, we have also derived and two very important equations. And in that, one of the not derived, but at least have mentioned, the one of the important equation was the junction potential. So, can anyone just tell me what exactly was junction potential? How do we understand about junction potential? What is the significance, first of all, like how it is created? How is the junction potential created? Anyone? Anyone? Junction potential, not studied. Hmm? You people are not studying at all. Later on, if things get piled up, I don't think you will be able to manage. I'm telling you. All right, it will be very difficult job for anyone. If anyone, if you are pending it with so many things, no, really it will be difficult. I'm telling you. Okay, so because if every day, if I have to repeat what I have done already on the previous day's class, I think that's the biggest drawback, I would say. So I told you very clearly that the junction potential is a very important segment of our discussion, because in each of the P and N type, if we consider as P and N type, suppose this is my P and this is my N. So the majority carriers will be the mobility, there will be holes over here, whereas here it will be the electrons. Okay, these are the majority electrons. On the other hand, when these junctions are created, something of this nature, whenever the P and N junctions are created, there will be a tendency that if I apply any potential over here, okay, any potential over here, the N will try to jump to this junction, okay, whereas the holes will try to go towards the other direction. And in that process, there will be a barrier, there will be a space charge region. We call it the space charge region over here, okay, space charge region, where there will be accumulation of the electrons and holes. And after a certain period, when these electrons and holes are recombining together and the excess electron flows in the opposite direction towards this direction, whereas the hole goes in this direction, provided that we are having a positive supply over here and a negative supply at this end. If this is the case, then what will happen eventually, that during this period, like in the junction part, there will be some minority carriers which will be completely naked, in a way that the electrons here, the whatever the holes concentrations were, they have already jumped in this direction. So what will happen, the electron which are the minority over here will be exposed, and similarly the holes in this right hand side of the minority carriers will be exposed. So in a way, the diagram would look something like, it should look like, if I can consider in this way. So suppose this is my electrons which are exposed, and this is my holes which are also exposed. Okay, and that in fact gives us some kind of a potential over here, and this potential was called as the barrier potential. This was called as the potential, or sometimes it is called as junction potential as well. Okay, and this is basically a potential that the diode would have based on the material that it's using, that it will resist the current flow. After this junction potential is reached, after that the current flow will continue in a better way, or if you can say in an exponential way. That in fact was shown in one of the graphs which I had shown you over here, and we had discussed this even in the labs. In fact, for one of the labs it already happened. So this is how, or even this characteristics, if you remember, so this was the characteristic that we had talked about, where that after the knee voltage or the threshold voltage, after that, after the breakdown voltage is reached, there will be a huge exponential increase of the current in the forward direction. If it is the forward bias is what we are talking about. Reverse direction or reverse bias also will have the similar kind of trend, and that will be a reverse bias current in that manner. So based on this only, we had come across this particular equation, that how do I calculate this junction potential? And that was given by Vt log of NaNd by Ni square, where this NaNd we had just defined on top of it, where they are the donor and acceptor ion concentration over here. So for a given question, if NaNd is provided to us, we can substitute the Ni over here. Ni is given by N into P, the intrinsic concentration, if you remember. Ni, okay, Ni square was equal to N into P. Which law actually states this? Ni square equal to N into P. Which law states that N into P, the intrinsic concentration is equal to Ni square? Name of the law? Anyone?
Mass action law.
Mass action law. This was called as mass action law. Okay. So based on that, we had come to this conclusion. So if we are substituting everything, we will get the junction potential of the particular material. And also in that context, we have also observed that this Vt, which is the thermal voltage, can also be computed. Why it is important? Because this will be a constant value of 26 millivolt. Most of the case, like it will be constant throughout. So as I told, like if you are not like even if it is not mentioned anywhere, you can consider it as 26 millivolt and you can compute the necessary calculation. All right. And keeping that in mind, we had also found out another equation, which is called as a diode current equation. That is when the diode is in forward biased or a reverse bias condition, what will be the effective current that we are going to get? And that was given by I equals to I naught e to the power V by eta Vt minus 1. Remember that I told you that this I naught will be the reverse diode current or reverse saturation current, if I had over here, reverse saturation current, as well as V is the applied source or applied voltage that you are observing. Eta is a constant which will be 1 and 2 with respect to germanium or silicon or germanium respectively, and Vt will be the thermal voltage, which is again 26 millivolt. And if I apply all the details, all the values over here, and for eta equals to 1, it was found out to be e to the power 40 V minus 1. Even this one, the second one that I had mentioned over here, this was with eta equals to 2. Okay, it would be 20 volt minus 1. And when we consider the reverse bias case, this voltage as it is applied as a negative voltage, so the overall scenario the equation would look something like this. And from here we conclude that this V, capital V, would be far greater than the thermal voltage, the 26 millivolt. And naturally what will happen, that e to the power minus V by eta Vt, this will be far less than 1, because it's a minus sign over here. So this will be far less than 1. So we can ignore the overall part. So what we are left with is I is equal to minus I naught, which means that during the reverse bias, the total current across the diode will be nothing but the reverse saturation current. So that's what we had discussed on previous day's class. But now the point is that this current I that we are talking about, the diode current that we are talking about, this is when we are applying the supply voltage, and how we are getting the necessary results out of it. So that's what it is. But physically there are if I consider this current, the diode current, if I call it, so this is where we start. This is all will be a class note, so please keep a track of it. There won't be any PPT for this. So two ways there are, like physically this current that we are talking about, happens due to two reasons. Okay, so one is called as the drift current. Okay, so this constitutes the total current, one, and the other one is the diffusion current. Okay, okay, so these are the two things. So drift current and diffusion current. Now, ideally, these two current, the add up to these two current will give us the total finding or the total value, if you can consider, of the diode current. Right. So the diode current equation, you have already observed that that is dependent on the applied voltage. But if you are look into the physicalities, like how the current is generated, that is these two reasons, the drift and the diffusion current, those are the necessary reasons why the diode current is generated. All right. So just to understand this a little bit, for that matter, we will discuss with respect, very simply what we will discuss is the first is the drift current. Now, what is a drift current? Drift, from the term itself, what you can understand is that whenever an electric field is applied to both these two mechanism works in two different aspects. All right. In general, if I consider with one word, if you have to just remember it, because it might create a confusion later on. Drift current is when we are applying the electric field, or I would say electric field. Okay, and that led to some kind of a uh, electron hole pair generation, okay, or charge carrier movement. All right. So if this is basically what is happening, and for that purpose, whatever the current we are generating, which is basically what we are trying to observe by using a diode, that we are using a diode on a circuit and we are applying a supply, all right, and the current is flowing. So the majority of the current is due to the drift current. So it is basically when the applied field is on a particular semiconductor or a PN junction, then the charge carrier starts to move. And that charge carrier, the movement of those charge carrier generates a current density. And that current density gives rise to the drift current. Got it? On the other hand, the diffusion current, if I call it in that way, we'll discuss it a little detail. The diffusion current is based on. Can you tell me the term diffusion? What triggers to your mind diffusion? You have heard the term diffusion also before. What does the term diffusion gives us? Anyone?
So the flow of charge from higher concentration to lower concentration.
Concentration. So irrespective of charge, it's basically the word diffusion means whenever there is a higher concentration and there is a lower concentration, it's always the law is that the higher concentration will try to flow towards the lower concentration. Simple as that. So basically based on the concentration, if I call it, of charge. So one is due to the applied voltage, applied field, and the other one is due to the concentration of the charge. So this is basically the two physical currents which constitutes the diode current. Now let's see one by one the drift current first, and then we'll look into the diffusion current. Now, in case of drift current, this is actually done, or the derivation of it is a little detailed, but at least we will understand that the current density J. So we are discussing the drift current because most of the numericals will come from this particular segment. So we know that the electric current in a metal can be represented by J equals to Q multiplied by N multiplied by mu multiplied by E, where Q is the charge, okay, charge of the electron, which is 1.6 into 10 to the power minus 19 coulomb. That's done. N is called as the number of electrons, as we know, or the electron concentration, concentration. All right. Mu is a new term. It is called as, please make a note, this is called as mobility of electrons. Okay, so mobility of electron and mobility of holes both are two important factors. By mobility, what we mean is the average, I'll write it in color, it is known as the average drift velocity per unit electric field. All right. So basically what I mean is that if I consider V as the velocity and if I consider E as the potential applied or the electric field applied. So mu can be written as V by E. This will be in fact one of the very important factor we are looking at. So it in a way the mobility you should know it. Why? Because the more the mobility, the more is the chance of electrons being generated as well as moving. Mobility is something where things are moving, right? So the more the mobility of a particular semiconductor or a PN junction diode, the better is the chance that the electron will flow much faster. And that in fact leads to the chance or the conclusion that more the currents will be generated at the output. So this mobility is you can observe. So if you take this as a proportionate equation, so basically we can say that the drift velocity, this V, drift velocity is proportional to the applied voltage. So the more the voltage you apply, the more will be the potential or more the velocity you will get. All right, and the mu is that constant. So this is basically called as the mobility constant. And E is anyway, I have told you already, E is nothing but the electric field that is applied. So this is given by the generic, this J actually, this J stands for the current density. We'll write it this way. Hopefully these words are not new to you. So this is current density. All right. Now, if this is the generic equation for current density, okay. So for if I consider the current density for the electrons, okay, for electron current density, okay, this is given by Jn. I'm writing Jn. Please make a note of this. Q into N, mu into N, mu N E. So this is the change I'm doing. I'm giving this as equation number 1. I'm repeating it once again. What I'm trying to do. This is the generic equation for any form. In fact, if you remember, this is nothing but J equal to sigma into E. Can anyone tell me what exactly is this equation called? J equal to sigma into E. This is actually Ohm's law. I remember this is Ohm's law. Ohm's law in point form we call it. So this sigma that you're looking at, that is nothing but this part. All right. So sigma is nothing but the conductivity of the circuit of the material that is used, which is equal to 1 by resistivity of the circuit also. So of the component for that matter. So this equation is actually replicated by this in terms of semiconductor, because we have a concentration that we have to look into N and also mu N, which is the mobility of the electron. Anyone having any doubt till this point? Anyone, please? Anyone, please? No doubt means there is some problem. Either you are not able to understand, or either I need to stop at some point. Please tell me frankly. Are you able to understand it?
Yes, sir.
Is it under? I am getting yes sir out of 60 students is very difficult to understand actually. Other students, are, wait, go ahead. Any doubt? Till this point, it is fine for everyone. Please, this is very crucial.
Yes, sir, it is fine.
All right. And keep all these equations intact. Please keep the equations intact. So what I'm mentioning is that if you consider a PN junction, you will have the electron moving or electron concentration. But as you remember, as I told you, that whenever there is an electron, definitely there will be a hole also. So electron hole pair, remember the term I have used. So if there is a electron current density, definitely other way around, there will be a hole current density as well. So that is given by Jp, and that will be nothing but Q into P, mu P and E. So this is another equation that I have to keep in mind. All right. So these are the two major equations that I'm looking at. One is the electron current density and the other one is a hole current density. So out of these two, if I get it, the total current density, simply total current density, which is J if I call it, that will be nothing but Q into E N mu N plus P mu P. All right. So this is This is what we are getting out of total current density. Now, if you observe that if I go back to the mass action law, so out of that, if it is an intrinsic semiconductor, we know that N is equal to P is equal to Ni. We can just, if you remember, it was Ni square. N into P was Ni square. So in a way, we can say that N into P is equal to Ni. If it is an intrinsic semiconductor where there is no doping, nothing has happened, pure P and pure N type. So this is basically equation. So N and P we can substitute in a more generic way, and the equation could look something like Q into E Ni mu N plus mu. So this is basically the generic current density equation. Okay. Sorry. This is the generic current density equation that you're looking at, considering Ni as the concentration of electrons or holes in an intrinsic semiconductor. So you can observe the conductivity, the overall conductivity. Basically, this is the overall conductivity. This Q, I'll write it once again over here. J equal to sigma I E, where I can say sigma I is equal to Q into Ni mu N plus mu P. So this is called as the overall conductivity. Overall conductivity of the semiconductor. All right. And this value, this J that you are looking at, all right, this J will be as a unit. This J will have a unit of ampere per meter square for that matter. All right. So this particular J that you're looking at, the one that you're looking at, this ideally will be the drift current density that we are all bothered with. All right. So if it is drift current, okay, so we are looking at when suppose we are this is the total current density. Okay, so this is the individual current density for electrons and holes, and this is the total current density that we are talking about. All right. So the total current density, if I may write once again the generic equation for the drift, because we are discussing the drift current, right? So the drift current can be written as J in general, okay, or J drift if I call it now. This will be nothing but N Q mu N. I'm just writing the generic equation plus P Q mu P E. So this is the total equation, or if I can say E and Q common, so N mu N plus P mu P. Please make a note of this, that this is my J drift current. So given the concentration of N and P, given the mobilities of mu N and mu P, and given the voltage that you are applying, you actually can find out what is the J drift. Why we are calculating J drift? If I go back to here, that the diode current has two components. The drift current is entirely dependent on the conductivity, and that depends on the voltage that is being applied. Clear? So that is basically the drift part of the current. Any doubt with the drift current? We'll go to diffusion right now. Anyone having doubt with the drift current? The total conductivity, how we are calculating it, and what is the final expression that we are getting? Please keep these equations very important. This Jn, mu n, this one equation number 2, and this particularly this equation number 3. Okay.
Can
Please.
you save this and post this in?
Yeah, I will do that. I will do that anyway. I'll save it and do it. For the time being, because I will not be able to relate otherwise. I'll send you everything. But for the time being, please keep a note of it, that these equations are important. Right. So this is basically these are the equations that we are looking at, but this is for the drift current. Now, as we are discussing the other one, that is diffusion current, which is based on the concentration, what will happen that whenever we just let's draw a very simple diagram like this. Okay, suppose this is my intrinsic semiconductor, be it a P type or an N type, whatever it is. So there might be some kind of a holes which might be present over here. Suppose this is a P type, and it will go downward, or it will die out. As it goes to the junction, it will die out. Why? Because as it goes near to the junction, this side there will be some kind of an N-type material. So definitely there will be some kind of a recombination that will take place. And as it will go on recombining itself, there will be a profile or there will be a mapping, if I call it, is something like this. Do you agree to this? Just that the concentration would go down like this as we move ahead. Do we agree on this point? This is concentration, suppose, of electrons or holes, whatever it is. This is where the concentration is more. But as we go towards the end, the concentration is going down because it is getting more and more recombined with the subsequent N type, as we have discussed as of now. All the majority is coming towards this state and it is getting recombined and all those things are happening. So naturally, the concentration of holes is going diminished manner as we go along with X, which is the distance. All right. So the concentration profile or a drop in concentration is observed in case of semiconductor, and this changes or this concentration profile change will initiate a current which is called as the diffusion current. All right. Should I repeat it once again? Diffusion current. Diffusion means diffusion current or diffusion process is basically where there is a movement of ion or liquid, gas, particle, whatever you call it, from higher concentration towards the lower concentration. Over here, in case of a semiconductor, what is happening? Irrespective of p type or n type, there will be a motion of the majority carriers towards the position where the number of carriers will be lesser. And it is quite justified because as we go on with a diode, the more we go towards the end, towards the junction, due to the recombination process, the number of holes will be definitely less compared to the position which is away from the junction, which is quite natural. So definitely there will be some kind of a profiling, some kind of a drop in concentration. So inside the semiconductor, there will be a current which will be generated due to the concentration of the particle. All right. So we can say, if suppose in this case we are considering the P, that is the P type material. So we can say the drop in concentration can be given by something like this, dP dx. Is it not correct? We are changing the concentration with respect to x. So we can say it's a differential change, which is dP dx, where x is the distance. X is the distance. So thus the motion of charge happens between higher to lower concentration, and this leads to some kind of a diffusion current. Now, how do I define the diffusion current? So for electron diffusion, let me take another different color maybe. The electron diffusion, this J n will be given as Q into, this can be proved, but we don't need the proof for the time being, given by dN dx, where this Q is nothing but the charge, as we know. And also you can see there is positive because it's a N type and we don't have any negative sign over here. All right. And dN, this is the constant. This is called as diffusion constant. Diffusion constant of electron. All right. So this will be given to you, provided to you. So this is the diffusion constant. And this dN by dx, dN dx, that is basically the drop in concentration of the electrons for the. Correct. So this is basically what we are looking at. And why this is a positive? Can anyone tell me why it can be positive? Why it is positive? I will just write the other way around. Okay. I'll also write the whole drop in whole concentration. Let's see whether you can come by comparing whether you are in a position to tell me the answer correctly. So this is my whole concentration. This is my, so Jn, this is my diffusion current due to electron concentration, and Jp over here is diffusion current due to hole concentration. Can anyone tell me that why this is positive and this is negative? Why the sign? What does the sign indicate over here? Is it not the case that holes are positive and this should have been a positive and the electron should have been a negative one? Can anyone be that inquisitive to understand and tell me intuitively that why it is a positive and negatives come? Come on, guys. Anyone?
So the
So the
concentration is decreasing in
Decreasing,
the.
decreasing. Correct, correct. Concentration is decreasing. So this negative sign is actually showing us the decrease in the concentration. Decrease in the concentration. That's correct. And this negative sign was there. But as we are considering the electrons and that itself is negative itself in charge, so this becomes a positive over here. So that's why there is no symbol presented over here. All right. So don't get confused while writing. Please make sure that you keep this in mind. All right. So this is my JP. This is my JN, but this is for diffusion. So what I'll do is I'll just keep this as prime because I have already defined J in the drift as well. So if I know this two, so the total current, I current, if I call it, okay, that will be the drift plus the diffusion together. So drift current, now if suppose I want to have it in terms of the electron, in terms of the holes. Suppose I want to find I current for the P type. Suppose I want to have P type. Because P type means that more is towards hole. So drift current would look something like Q P mu P E minus Q dP dP dx. So this will be my total current with respect to a P type. So QP mu PE, hopefully all of you have understood that this is I have taken it from the equation over here. Or rather not here, I would say here. QP mu PE because we are specifically focusing on the uh, P type or P type. If it is an N type, same thing will happen. So that will be QN mu N E plus Q of dN dN dx. So this will be for N type. Understood. So this is the total discussion on the current density and how the total overall carried the overall nature of our calculation would be done with respect to the concentration of electrons, concentration of holes, concentration of the current density, and how we can evaluate all the same. So let's do some small little questions on this, numericals actually, so that things and the equations becomes a little clearer. So please make a note of these questions. First question that we are discussing is that at 300 Kelvin, the intrinsic carrier, the intrinsic carrier concentration of silicon is equal to 1.5 into 10 to the power 16 meter is 3, okay, cubic meter. All right, so this is the electron intrinsic carrier concentration. I'll explain it one by one. Now question is, if the electron and holes mobility, okay, mobility are 0.13 and 0.05 meter square volt second, like this, okay, respectively, determine the intrinsic resistivity of SI. Determine the intrinsic resistivity of silicon at 300 Kelvin. All right. So the question is, as mentioned over here. So let me try to understand the question and to answer it. All right. So the thing is, we have to, what we are observing over here, the question is to find the resistivity. Okay. So till now, we haven't come across the equation of resistivity, but we actually know what resistivity is in terms of the conductivity that we have. So if you remember that, if I go by the solution, if you remember that we have already established that sigma I, or the, if you can consider the conductivity, is given by, it always will be 1 by Ri. All right, where Ri is the total resistivity of the circuit. So somehow, if we can find out what is sigma I, we can find out what is Ri. We can take the reciprocal of it and we'll get it. So can anyone just quickly tell me from the equations, whatever we have discussed so far and whatever you have noted it down, how do I estimate this sigma I? How do I compute this sigma I? Sigma I is the total conductivity of the device, semiconductor device over here. Is there any equation that we have discussed so far that gives us an understanding of the sigma I?
J equal to sigma E.
Sigma I equals to anyone?
Q into N into mu.
Q into N into mu. Achha, let's see. So will that be fine? Sigma equal to Q E N mu. Will that be okay in this equation? Anyone? Anyone wants to add anything over here?
Q and U and mu only.
The answer, yeah, please. Someone was, I think.
Charge into concentration into mobility.
That's fine. The point is here, the one that I have written over here based on your input, this is not the overall conductivity. This is only for the electron concentration, I can say. Electron conductivity. But you have to add the whole conductivity as well. So if you go back, if I go back a little bit up, and if you say check here that this sigma I that I have mentioned somewhere over here. All right, this is here. Sigma I was Q into Ni multiplied by mu N plus mu P. So this was the total concentration, total overall conductivity. So basically, Ni is where you are actually including both the concentration either in terms of holes or the electrons. And you are assuming that the mobilities of both the mobility of electron as well as holes are known to you. So in this equation also, you can observe in this question also, electron mobilities, both mobilities are present. So what we have to do is, instead of this equation, we might just change a little bit, where we can use Q of Ni multiplied by mu N plus mu. Understood why I did it? The sigma that most of you were looking at, they were only for the hole or the electron. But what we have to consider is for the overall semiconductor. So for that, we have to consider the equation Q Ni mu N plus mu P, and you substitute the respective equations and you will get the necessary value of sigma I. So if I'll just quickly do it, because this calculation is where you might make some mistake. So 1.6 into 10 to the power minus 19. So that is for the Q. Okay, Ni is basically the intrinsic concentration. Already I have mentioned over here, which is 1.5 into 10 to the power minus 16. Please be very careful with the data while handling it. Okay, this is 16. Okay, then bracket mu N plus mu P, which is 0.13 plus 0.05 as provided over here. So finally, what we are getting is something like 0.432 into 10 to the power minus 3 Siemens per meter. So this is about the conductivity. If this is conductivity, we are having Ri, which is 1 by sigma I, and that will be 2.315 into 10 to the power 3 ohm meter. So this is by resistivity of the circuit. So this is where the equations or the question type will come in, and the equations that I have discussed so far will be handy. All right, so this is one type. Okay, let's quickly do the second one. As I'm trying to accommodate as much any question as much possible. Second one, if I look at, find the concentration of donor atoms See this. Find the concentration of donor atoms, okay, to be added to an intrinsic germanium sample, okay, to produce an N-type material of conductivity 480 S by M, given mu of N is equal to 0.38 meter square per volt second. So the question is, find the concentration of the donor atom. Can anyone tell me where do I start off with this? Can we have an idea about this? Whether we are in an understanding of this segment?
So we can just reverse the formula that we just used.
Absolutely, and we have to only keep in mind here it is an N-type material. All are N-type material. So basically we have a majority of electrons in this. So ideally as the intrinsic semiconductor if we are looking at and as we are looking at donor atom, so basically we are looking at Nd. Okay, so that's a donor atom, donor concentration that we are talking about. So if we consider with respect to sigma n, if I consider, so that is q into n into mu n. So this is what the concentration, only the if I consider for the electron concentration, if I can't do it, and this n, okay, this n is the donor atom. So this is q into nd as per our requirement into mu n. All right, and so this is given by, simply we can find out what is sigma. So nd will be concentration sigma I divided by q into, and finally we can get the solution. All right. So again, it's the same question, same equation, only that the constant based on the previous question was we were trying to find out the conductivity. From that we found out the resistivity, but the charge, the concentration, and the mobility were provided. Over here, the mobility is provided, the concentration that makes it an N-type, that is provided. That means the excess electrons or the donor concentration which is there, and the charge with the electrons are known. But the question over here is to find out what is Nd, the excess that you have to apply in order to make it N-type. All right, so this is another second type of question that you might expect. And let us finish off the third one, just to at least I'll give you the statement at least so that you can do it on your own. For example, find the conductivity and resistance of a bar. Let me just write it down in this way. Find the conductivity and resistivity. I need an answer for this actually, okay? Or I would say resistivity. No, I would say resistance, not resistivity. So resistance of a bar of pure Si silicon of length 1 centimeter and area 1 meter, 1 millimeter square at 10 to the power 6, sorry, at 300 K, at 300 Kelvin. Given mu n is equal to 0.13 meter square volt second, mu p equals 0.05 meter square volt second, Ni equals 1.5 into 10 to the power 16 meter cube, that is in this way, and electron charge is 1.6 into 10 to the power minus 9 coulomb. Question is find the conductivity and the resistance of a bar. I want you to note down this and send me the solution after doing the calculation from the equations that I have mentioned today. Only the thing is, can anyone tell me a equation by which we actually can find out the resistance part over here? How do I relate to this?
R is equal to L by A.
Yes, R is equal to L by A or something like this. We can say resistivity. We can say this is 1 by sigma. This is resistivity multiplied by L by A. So that's gives us the resistance. So you can observe resistivity we have just now found out in another question. So the same way, similar questions can be extended one after the other, but the equations and the calculations remains almost the same. All right, so hopefully this is little exhaustive to all of you, but I guess all of you would go back to the materials and we'll study this properly, so that in next class when we come in, we can start off with another new segment of our discussion. So I would request all of you to please go to the material, and if at all you find anywhere any problem, please let me know. Also, please solve this particular question and send me over chat. All right. So I'll stop recording for the session as well as